person. That is, a person with a good height and a fair amount of weight is considered well built. But this concept again is fuzzy. So the idea is, where do we put our decision boundary? Where do we draw a line? Okay, so that is the point. Okay, now we will also come to algorithms. We'll discuss algorithms in general. And do you know who this gentleman is? This gentleman is actually Mr. Algorithm. He was Al-Khwarizmi. He was a mathematician and scientist in what is present day Baghdad. And in fact, the term algorithm is an anglicization of Al-Khwarizmi. Okay, this gentleman's name. So he is actually Mr. Algorithms. He is an ancient Persian mathematician and astronomer, and he's got lots of contributions to basic maths and science. One of his treatises was named Al-Jabr, and this an anglicization of the term Al-Jabr resulted in the discipline which today we call algebra. And he's got lots and lots of very fundamental contributions. For instance, the solution to a quadratic equation, that is his. Then he also recognized that the highest degree equation which can be solved in a general form, in a closed form, is 2, which is quite disappointing. But then, yeah, that is true. Like a cubic equation or equation of a higher degree cannot be solved in its most general form in a closed form, and one often has to take recourse to iterative or numerical algorithms for that. And then there are lots of other things which we in today's world we take for granted, but they are due to Al-Khwarizmi. For instance, if we take a term from the left hand side of the equation and take it over to the right hand side, what will happen? The sign changes. So positive sign, if it is there on the left hand side of the equation, if we take it to the right, it gets appended with a minus sign, and vice versa. Then if we have something in the numerator on the left hand side, if we take it to the right hand side, it comes in the denominator, and vice versa. And more, and of course, yes, he brought the concept of Indo-Arabic numerals and decimals to the West, okay, the Western world. So, and in terms of what we are doing, one of his basic observations is that if we have to solve a problem with a set of steps, then that set of steps needs to be finite. Okay, this is the basic characterization of an algorithm. Okay, we started with a slightly filmy touch. I had mentioned that the general formulation which is used today for unsupervised learning for k-means is due to McQueen, J.B. McQueen, and we took a slight filmy touch there, and because as Indians we are sort of crazy with Bollywood and Hollywood and all of these, so we've taken an example from the films. Here again, I like to characterize algorithms into 3. Okay, yes, the good, the bad, and the ugly. Okay, so it's not as bad as this movie, but yes, the algorithms which I see fall into the good category are those with polynomial time complexity. That is, if the size of the input is n, okay, if the input to the algorithm is an array of size n, then if it takes time which is order of n to the power some constant k, then it is a polynomial time complexity algorithm. These algorithms would be said to be good. For instance, all sorting algorithms like bubble sort, selection sort, insertion sort, their order n square, they'll be said to be good. There are more efficient comparison based sorting algorithms such as quick sort, heap sort, merge sort, which are better because they're order n log n. But n log n again can be upper bounded by n square. So we'll still keep them in this category, order n to the power some constant. Then with regard to signal processing, the DFT, okay, wherein we say that the DFT, capital F of u, is, let's say, 1 by n sigma summation x equal to 0 to n minus 1 f of x e to the power minus j2 pi x by n. So this has time complexity order n square. So we'll still say this is a good algorithm if one is using an FFT based formulation that has time complexity order n log n. That is slightly better, but they are still good algorithms. Okay, yeah, this is exactly what I had mentioned. But then all algorithms are not that good. There are algorithms which fall into the category which I call the bad. These are algorithms with exponential time complexity. These are the algorithms which typically fall into the class which is typically called either NP hard or NP complete, wherein the time complexity is a constant to the power the size of the input. So if the input is an array of size n, then the time complexity is some constant to the power that input size. I'll give an example. For instance, suppose one has n Boolean variables. So how many min terms can one have with n Boolean variables? One can have 2 to the power n min terms. For instance, for two variables, one can have 4 min terms. Okay. Now, in order to construct a Boolean function, one needs all possible permutations and combinations of these min terms, and given let's say x min terms, how many possible functions can one have? For instance, with 4 min terms, m0, m1, m2 and m3, how many functions can one have? It is 2 to the power 4, that's 16. So effectively this is 2 to the power 2 to the power n. So this has exponential time complexity, and if one needs to do digital function design, this is something that one cannot avoid. One cannot avoid the time complexity that is associated with these. Okay, so that is the idea. So there are lots of practical situations where the time complexity of an algorithm, it may be exponential time, but they're practical. We cannot really avoid them. Some other instances are like the traveling salesperson problem, or anything that is based on tree search, for instance, has exponential time complexity. Now, typically problems here fall into two categories. They are either NP hard or NP complete. NP stands for non-deterministic polynomial. NP complete problems are slightly better because one problem here in this set can be converted into another problem in this set in polynomial time. So if, for instance, somebody comes up with a polynomial time algorithm solution for one of these problems, it means that we should be able to solve any one problem in this set, and in fact all problems in this set in polynomial time. That is the promise. So this is the set of NP complete problems. On the other hand, the set of NP hard problems is worse, because even if some genius comes up with a solution to one of these problems in polynomial time, these are problems which cannot be converted into another problem in this set in polynomial time. So even if one solves one of these problems in an efficient manner, one comes up with an efficient algorithm for one of these, there is no guarantee that there is an efficient solution for any other one out of this set. So yeah, these are some of the examples that I had also specified, that is Boolean functions of n variables, min terms and combination of min terms, 2 to the power 2 to the power n, then the traveling salesperson problem, and so on and so forth. The third category is something that I call the category of ugly. These are algorithms, these are typically numerical algorithms. They will converge to the optimal solution with probability 1, but unfortunately they'll take an infinite amount of time to do so. So what best can we engineers do about it? So one typically lets the algorithm run for a long period of time, and then we have a look. If it achieves some optimization criterion after a long period of time, then we will stop the algorithm, because we can't let it run on forever. So these are ugly, these are the category of ugly algorithms. Now, this is my nomenclature, so don't read too much into this. But the idea is that there are many practical solutions where we cannot avoid these sort of algorithms. And unfortunately, in machine learning, most algorithms fall into the category of either the ugly or the bad. That is the unfortunate part. Now, in the k-means algorithm, we will interestingly see that this is one of the few algorithms that can actually, in a good case, we will talk about this, in a good case, can be solved in polynomial time. In fact, very nicely in linear time. That is something that we will see. Okay, now let us take a mathematical perspective into the problem that we are looking at, the k-means algorithm. We are given a set of points, typically a very large set of points, x1 to xn, and n is typically a very large number. These are points in d-dimensional space. Now these need to be grouped into capital K groups or clusters, okay, where capital K is typically much smaller than capital N. In such a way, we'll need to group all of these points into K clusters in such a way that after that we will select one point from each cluster and say that this is a representative point of this cluster. Okay, we will say that this is the prototype vector. So this is vector quantization. This is the essence of VQ, vector quantization. It could be the cluster centroid. Okay, so mu j would be a prototype point for the jth cluster. And since we want some mathematical formulation, we will take a mathematical formulation, we'll try to solve an optimization problem. And a very natural way to solve this is so that the squared distance from these prototype points, okay, y squared, because we want to treat positive and negative differences in the same way, and we don't want to take the absolute value. Why don't we want to take the absolute value? Because the absolute value of x is not differentiable at x equal to 0. So we typically want to avoid such problems. So one possible optimization function is that, optimization criterion is that the sum of squared distances of each data point to its closest prototype vector should be a minimum. That's the idea. And in vector quantization, as those of you who work in speech and audio would already know, these mu j's are called the codebook vectors. This is what I had mentioned. And we will formulate this in a mathematical sense, and we will propose an objective function which we will try to optimize, and this objective function we will call it a distortion measure. But before that, let us take a diagrammatic view of what the problem at hand is. Okay, so you can see this example in two-dimensional space. What is the intuition? Intuition tells us that there are three groups or three clusters of points in two-dimensional space. And suppose we color these. So one of these is the red cluster, one of these is the blue cluster, the third is the green cluster. Our job at hand is to take a piece of rope and gather together all points in the green cluster, another piece of rope and gather together all points in the blue cluster, another piece of rope and gather together all points in the red cluster, And for each one of these clusters, identify the decision boundary and designate a representative point, which we will call the codebook vector or the prototype point. Okay, so this is, if you remember that example on the division of states on a linguistic basis in India. So it is something like taking the geographical coordinates of a city, okay, the latitude and the longitude, which are two coordinates which represent a city, and then take as a feature vector the languages spoken. So the idea is that we want to cluster together all the Telugu speaking people into one state. Of course, that is not true nowadays with Andhra Pradesh and Telangana being split. But then, yeah, in general, that is the way that this was done. So the region of most people who speak one particular language, they should be put into the same region. And we know that we will make a mistake. So on the other side of the border, also there would be people who would speak the same language, but then this should be an optimization function in some way. So this error has to be minimized, and at the end of the entire process we would want to designate a representative point for each cluster. This may be, for instance, the capital of the state. Okay, the capital of the state could be a codebook vector, it could be a representative point. Of course, for the capital of any state, it could have other parameters as well. The locatability, the means of transport, is it a economic center, is it a center of economic activity, so on and so forth. Here we will like to look at a more mathematical formulation. But so this is as such a pretty rough example. So one way to put this as an optimization problem is to formulate what I call a distortion measure. So if you look at the right hand side, so this distortion is the sum total of all of these errors. There are two summations. One summation is for all points, which is perfectly reasonable, for I equal to 1 to capital N. Okay, so for all points, I want to calculate this quantity, and not just for all points, I want to do it for all clusters as well. I want to do it for each of the k clusters. And what is this function that I need to optimize? If you look at, let's first look at this term. So this is a square of a norm or an absolute value in this case. This is the distance of the point from a prototype vector. So this is the squared distance of point I from the jth prototype vector, and Rij. Rij is a binary indicator variable which is 1 if point I belongs to cluster J and is 0 otherwise. So what is the idea? We have to minimize this distortion, so to say. Okay. So in general, our clustering should be such that we should get dense prominent clusters which are as far apart from each other as possible. That is the general intuition. And so we have to optimize this in such a way that the optimization function is to find the parameters. What are the parameters of this particular function? The parameters are the unknown quantities. The parameters are the Rij, that is the binary indicator variable, which point would be assigned to which prototype. This is the clustering that we are looking for. And to calculate what these prototype vectors, that is the representative vectors for each cluster, what they would be. So the optimization problem, now we have a problem in the mathematical sense to estimate the parameters, which are the Rijs, the binary indicator variables, and the cluster prototypes in such a way that this distortion measure is minimized. Okay, so now we have a mathematical formulation of the problem. That's the idea. Okay, so yeah, this is what I had just mentioned. that is the binary indicator variable, the one that I've shown in red here. This is 1 if the ith data point is assigned to the jth cluster and is 0 otherwise. And the idea of the optimization here is to find the set of parameters. What are the set of parameters in this particular function? The set of parameters is all the binary indicator variables Rij and the prototype vectors mu j, where j varies between 1 and capital K, in such a way that j is minimized. Now, one way to solve this is in two logical parts. This is also called the expectation maximization framework. We will see what the expectation maximization framework is, but let us just look at it in let's take an intuitive explanation for this. The idea is to fix one set of parameters, optimize with respect to the other set of parameters, then after a couple of steps to fix the first set of parameters based on whatever value that we had got in the preceding steps, and to optimize with respect to the second set of parameters, and then alternating till we have some form of convergence. Now, one very natural question would be, why do we do all this? Would it not be better if the problem were linear? Let's say we have a set of equations which can be described by ax equal to b, where x is a vector, b is another vector of the same dimension, and a is a matrix. Then if this particular system matrix is invertible, then we'll say that, well, why don't we directly take x equal to a inverse b? Now, even for a linear problem, even for a nice and linear problem, wherein the matrix A is square and it is full rank in the best of circumstances. Okay, in general it'll be rectangular, and it'll obviously not be full rank, and there we will not be able to take the inverse of a matrix. So what we'll end up with is a least squares solution, something like a pseudo inverse. But then let's assume the best case scenario, wherein this particular matrix is square, it is full rank, it is invertible. So why don't people directly calculate the set of variables to be x equal to a inverse b? Yes. So all our friends from control theory would also start shouting, well, we can't do that in most cases, especially if A is a large matrix. Why? Because the time complexity of trying to invert a large matrix numerically is considerable. Okay, not just the time complexity, the space that would be required in terms of the memory requirements would often not be practical. So even for a linear problem, it is often not feasible to solve it directly. So what does one do? One divides the set of parameters into two or more parts. The easiest way to is divide it into two parts, fix one of them, optimize with respect to the second smaller set, and in the second phase to fix the second one and optimize with respect to the first one. Okay, so in this case we can first choose, take an initial guess for the k initial cluster centroids mu j, and once we have fixed these mu j's, we can find the binary indicator variables. We can find the assignment Rij. This is called the expectation phase. We will see where and why these terms come in. The second phase is whatever we found earlier, the binary indicator variables, we fix them and we optimize with respect to the cluster centroids. So this is called the maximization phase. We will see why these are assigned these particular terms and what happens here. And we repeat the others. We repeat these above steps till either there is convergence or we have reached a fixed maximum number of permissible iterations. Now the interesting part here is that every one of these steps for k means is provably convergent. This is not probably, this is provably convergent. Okay, please excuse me for this particular typographic error. So provably convergent means we can prove that these are convergent. Okay, and this proof is not very difficult to see either. Let's look at the first step, wherein we have fixed our cluster centroids or our prototype vectors, and we minimize with respect to the binary indicator variables. So what happens here? So if we write this expression, we'll see something interesting. We don't even need to do an optimization here. We can do it by construction. So for a
Sir,
point, yeah, please go ahead.
sir, what is this symbol equal to and above that the triangle? Actually, what this symbol is?
Okay. This symbol is defined as, all right. So this is the way we are defining this function g. Okay, so this is often in some textbooks you'll find a def written on top of this equal to sign. This just indicates that we are defining this particular function to have this expression. That's all. Is that all right? Sorry, I should have mentioned this before. Is that all right?
Yes, sir. Thank you, sir. Means it is
Okay.
defined like this. Huh? It's not equal, but we are going to define. We have to read
Yeah,
that
it
way,
is
na?
is defined as
Yes,
is defined
defined way.
as.
Yes,
Yeah.
sir. Thank you, sir.
Thank you. Thank you, Dr. Mishra. Okay, so we assign it to the closest cluster centroid. That is, in other words, we put Rij equal to 1 for what is called the argmin. So argmin just means that if this minimum occurs for a certain value of j, let's say L, then we want that argument for which this function gets to a minimum. That is, we put it equal to 1 for that particular j, which achieves a excuse me, minimum. That's the idea, and it is 0 otherwise. So we can do this by construction. And the second step is also provably convergent, because if we write this expression, this is the way we have defined it. This is quadratic in mu j. Excuse me. And if we take a partial derivative with respect to mu j, the set of parameters, this is the standard way in which one does optimization. That is, take a partial derivative with respect to a variable or a set of variables, a vector of variables in this case, set it equal to 0. What will happen? So as you can see here, I can break this summation up. The inner summation will have only one term which has mu j. So there will be the first term, the second term, the j minus 1th term, jth term, j plus 1th term. So there will be one jth term. So the only one which will have a non-zero partial derivative is this one. Okay, and most rules of vector calculus seem to mimic those of scalar calculus. And if we just distribute the terms around and take things which are positive to the left hand side and take things which are negative to the right hand side, so that everything becomes positive, then this is what we are going to end up with, and this gives us a nice result. If you just solve this, this is pretty straightforward math. The result is interesting. So mu j at the optimum would turn out to be the weighted average of all the xi's. This is interesting. Let us see the physical significance of these terms. What is Rij? Rij is an indicator variable. It is one if point I is belongs to cluster J and it is 0 otherwise. So what is the denominator for this? The denominator here is actually the number of points which are there in the jth cluster, because this term is 0 for terms which are not in the cluster. So if we add them up, so this is nothing, the denominator is nothing but the number of points in the cluster, and the numerator is simply, it is the sum of all the points in the cluster itself, because all others are 0. So what is this? This is the mean. So for a particular cluster, we have simply added the points and divided by the number of points. So in fact, this is the reason why this particular algorithm is called the k-means algorithm, which says that at the optimum, what we end up with is the cluster prototype vectors being the means or the centroids of the corresponding clusters. So let us see what the steps in this algorithm would be. So algorithm K means there'll be an initialization. We'll talk about this, what might be a possible initialization, what might be the time complexity of this initialization. So the idea is to, it may be random. Let us fix the cluster prototype vectors. We can do this in many ways. We can take k points at random, or we can take the first k points and then gradually update our cluster centroids. But in some way, yeah, this could be arbitrary. The expectation step is we have fixed these prototype vectors, and from that we find the assignment, we find the values of the binary indicator variables. And how do we do that? You've seen that we can do this by construction. That is, we assign each point to its closest cluster prototype. And what we have shown before is that this function is non-increasing. Okay, one expects that this will be non-increasing. The second is the minimization step, wherein we have fixed the assignment and we recalculate the prototype vectors. We recalculate the cluster centroids or the means. And here we have seen above that this process of optimization is going to minimize this. Okay, so each step is provably convergent. And we repeat this till either there is no change in assignment across two iterations, or we have exceeded a certain maximum number of iterations. So this algorithm is provably convergent, but unfortunately this is an issue. It is guaranteed to converge, but there is no guarantee that the function at hand is convex. So it is only for convex functions wherein every optimum is a global optimum. So in this case, we might get stuck up at a local optimum as well. That is the difficulty that is associated with this, but we are willing to live with this. Okay. All right. Let us see an illustration. So this example I've directly picked up from the textbook on machine learning by Christopher Bishop. And so what do we see here? What does intuition tell us? Intuition tells us that there are two clusters here and one here. And let us make an arbitrary initialization. So there are two clusters, we'll call them the blue cluster and the red cluster, and we will initialize our prototype vectors to be somewhere in space. This is completely arbitrary. So what is the first step? The first step is to assign every point to its closest cluster prototype. So in other words, we have to color these points based on whether, based on the color of the prototype vector it is closest to. So this is what one obtains as a result of the first step. So points which are closer to the blue cluster prototype vector would be colored blue. Points which are closer to the red cluster prototype would be colored red. That is the idea. Okay, so this is the first step. The second step is to recompute the cluster centroids. So if we recompute it, one expects that the cluster centroids would come inside the cluster. This is the idea. Okay, this is one iteration of the two phases. Next iteration, again, we assign each point to its closest cluster prototype. So this is essentially what we end up with. So we have assigned each point to its closest cluster prototype, and after that we recompute the cluster prototypes, and we let this run for a couple of iterations. And what you find is that, well, at the end of a couple of iterations, the algorithm has converged. That is, there is no change in the position of the cluster centroids, no perceptible change, or equivalently, the value of the function which we are trying to optimize, that does not change drastically across two successive iterations. So we stop here. Okay. So there are some points. First is a problem that I happened to mention earlier as well. That is, there is no guarantee that this function is a convex function. So it could converge to a local optimum, a local minimum, which need not be close to the global minimum. Okay, that is a problem, but that's not really something we can help. We will see this. So suppose one had an option of running, if one had a good amount of compute power. So what happens if we exhaustively evaluate all possibilities and then pick the minimum? Then we would be guaranteed to get to a global minimum, right? So let us consider all possible initializations. Then how can one do an initialization? We can either take a random subset of size k of the data points as the cluster prototypes to start off with. And suppose we do that, then how many possibilities can we have? We have n choose k possibilities for this initialization. Now n choose k by Stirling's formula, that is exponential in n. So that itself tells us that the time complexity of trying to find an optimum here would be exponential. Okay, so that is slightly disappointing. But then what is a bit more disappointing is the fact that it is not necessary that the initialization is limited to a random subset of size k. We could take any initialization, and that unfortunately we have an infinite number of choices. Okay, so that is the difficulty associated with it. So if one had that outer loop of choosing a subset, then it could have an infinite time. But then what is the saving grace? The saving grace is that we will like to apply a k-means algorithm which to data which has some natural clustering. If it doesn't have a natural clustering, then it may not be a good idea to apply it to that set of data points. All right. Okay. The expectation step is, let's look at the time complexity of each one of these steps. In the E step, we need to calculate the distance between every data point and every prototype vector. So the time complexity is, there are n data points, there are k prototype vectors. So the complexity is n into k. And if k is a constant, okay, then this is linear in n. So this is order n. And the maximization step is a linear time operation. Why? Because all that we are doing is we are finding an average, and it takes order n time to read in a set of points, add them up, and then divide by the number of points to calculate its average. So every step is has polynomial time, and in the best case it has linear time. So that is why this particular algorithm, that is why we had that PJ about Lightning McQueen, that is, this particular algorithm is blindingly fast. Okay, and this is the meta loop that I was talking about. So we can let it run for each of the n choose k possible seed points, or let it run till a certain maximum. Or very practically, what one could do is we could run it for a few values of k. Typically, k would be a small number, so we can run it for certain k and then select that one which will have a minimum. That's it. So practically, this is what one can do. And here we also talk about the second formulation, the alternate formulation of k-means, which works with a distance threshold. So where is a possible use case of such a formulation? A possible use case is something like, let's say, in what is called rational drug design. The idea is that typically today, how does one make a new drug? One makes a new drug typically not using a wet chemical engineering process. Why? Because in wet biochemical engineering, one has to often deal with some reagents, some chemicals, which it may not be very safe to deal with those chemicals day in and day out. The second reason is that these chemicals are very costly. So we want a cost effective method. So what one typically does is one does it in bioinformatics, one does it in simulation mode. So what one wants to do is to find clusters of, for instance, for proteins, these are amino acid residues. So these are typically clustered. These are what are called, my friends in biochemistry say that, in biotechnology say that these are called active sites. So these are the sites where the binding takes place. Okay, so these are typically clumped or clustered. Now, how does one find these when one does not have any idea of what K could be? So the alternate formulation is with a distance threshold. And the K means formulation that we had done before is, as such, it is a batch algorithm. This is not online. That is, as data is coming in, it cannot operate like that. So this alternate formulation has a distance threshold. For instance, a distance threshold for the amino acid residue clustering problem is 3.6 angstroms. So in fact, this 3.6 angstroms is a threshold which has biological significance. That is, points which lie within a radius of 3.6 angstroms. They they form these active sites. So the way that this works is, take the first point, put it into its own cluster. Take the second point. So if the second point lies within 3.6 angstroms of the first point, then say that it belongs to the cluster that is associated with that. And if not, create a new cluster prototype out there. That's the idea. Take the third point. So if there are two clusters already, then we take the distance, we calculate the distance from the two cluster prototypes, and then we assign it to whichever one is less. And what if there is a tie, that is there the equidistant, we can do this arbitrarily because we are not going to penalize this optimization function in any way. The value of this optimization function is going to be the same. The fourth point comes in. So then again we do this just as data is coming in. So this is an online algorithm. Okay, so this is an online algorithm. This will work as data is coming in. In a sense, this is an alternate formulation wherein the variable is not k, the number of clusters, but the variable in this case is a distance threshold, okay, which we are taking out here. That's the idea. Ah, okay. Then there are limitations of this particular algorithm. One important limitation is there are some cases where this algorithm is not guaranteed to work. For instance, what happens if data is organized into concentric circles? This is a classic example that is given in, if you're familiar with the kernel trick, which is used in machine learning, typically in the SVM formulation. So there are two classes and both are in concentric circles. Then what happens? So in this case, the algorithm is not guaranteed to work for the very simple reason that if they are concentric circles, the means of the two classes is going to be that same center. So there is no way one can separate these two classes. So this is one example where this is guaranteed not to work. However, people often use k-means as a precursor to data processing. They first use k-means because of the nice complexity associated with it, and then in general visualize this typically in a lower dimension to find out whether it is possible at all to do this optimization, to is it worthwhile checking for clusters. If not, one applies some other sophisticated algorithm with a greater time complexity. How can one generalize this formulation for k-means? Rij, we took Rij as a binary indicator variable, 0 or 1. So in general, we could generalize this Rij to not just be 0, 1, but to take on a value which lies in the range 0 to 1. So we could give it a probabilistic connotation. Okay, a number between 0 and 1 can be assigned a probabilistic connotation, or it can also be a fuzzy formulation. That is, we have a membership value. So the difference between probability theory and fuzzy logic is that a particular point could belong to more than one class, each associated with a membership value, and there is a proper calculus, which is a proper algebra which goes with fuzzy with the fuzzy system theory as well. So there is a generalization, and then there is also the part about, so instead of means, one could extend that to some other central descriptor of data like the median. So instead of calculating the means, one could also try calculating the medium. So there are lots of other variants like the k-medioids problem or fuzzy c-means. So the essential idea is that they're all based on the same ordinary plain vanilla k-means algorithm. Okay, so at this point, we will change gears slightly. We will go to a related problem, which is a mixture of Gaussians. We will go to a problem of curve fitting. And here we will see that, sorry, this is an observation that is almost any parameterized curve can be fitted to any bunch of points with an associated error cost. Okay, this is something that is always true, and it's something like, suppose we have a two-dimensional distribution of points which are distributed in two-dimensional space. So in this case, it is possible to fit a line. Now if that distribution of points is cigar shaped, okay, then we have some visual evidence that, okay, the model in this case fitting a line would be a reasonably good model. Now if those points were distributed uniformly across 2D space, please note that we would still be able to fit a line to those set of points. However, it will be a bad fit. Why will this be a bad fit? Because the average perpendicular distance, let us say, of any point from that best fitting compromise line is going to be much higher than what it would be for a cigar shaped distribution of points. Okay, so this is an important take home point. Almost any parameterized curve can be fitted to a bunch of points with an associated error cost. Okay, why are electrical engineers completely besotted with the idea of a Gaussian? A Gaussian is computationally nice. Why is a Gaussian computationally nice? It is nice because it is a distribution that is completely characterized by two parameters. Which are the two parameters? The parameters are the mean vector and second is the covariance matrix. And these happen to be the first and the second order moments of the data. So a Gaussian is nice because it is completely characterized by only two sets of parameters. The two sets of parameters are the mean and the covariance matrix. Okay, there is no other variable here. And how does one, so suppose one is given a probability mass function. So how does one fit a set of Gaussians to that probability mass function? So anywhere one sees a hump or a bump in the probability mass function, one can put a Gaussian out there. And so that is fine because there would be humps and bumps all around. But what about a constant region? How do we approximate that? So for this, we use many closely spaced Gaussians. So that if the contribution from one Gaussian comes and then it decreases, we start another Gaussian from that point, so that the contribution of the second Gaussian increases as the contribution of the first Gaussian decreases. So we can approximate a constant region with a slowly undulating region, okay, of many closely spaced Gaussians. So the take home point here is that we can fit almost any distribution, sorry, we can approximate almost any distribution with a set of Gaussians. That's the idea. So let's take a couple of visual examples. So suppose this is the probability mass function. We can still fit one Gaussian. So if our model is one Gaussian, we can still make a fit. However, this is a bad fit. Why is it a bad fit? Because the most probable region, see, in a Gaussian, there is a very important property. What is that important property? The important property is that the mean is the same as the median, is the same as the mode. What does that mean? What is the mode? The mode says that most samples of the Gaussian should come from a small region around the mean. We know that result, right? That is the 99.97% of the mass of a Gaussian is concentrated between plus minus 3 sigma for a one-dimensional Gaussian. So in this case, while we have still been able to fit a Gaussian, this is obviously not a good fit because there is hardly any sample which is from around the central descriptor, which is the mean, the median, or the mode. Let's try another model. So what about two Gaussians? Okay, so this is a slightly better fit. So from 1G, one goes to 2G. This is a better fit because every hump or bump, we have fitted a bell-shaped curve. We have fitted a Gaussian out there. Okay, so 1G, 2G, from where, where are we going? We go to 3G. 3G as not in the communication technology, but then in this case, this is we are taking three Gaussians. Okay, so suppose this is the red Gaussian, this is another one, this is a green Gaussian. Let's take another one, which is a brown Gaussian, and then we simply add them up. Now, if we add them up, there is a problem. What is that problem? If we add them up, the problem is, there is a speed limit which we have exceeded. Now the speed limit in probability is 1. All right. So if we happen to sum probabilities and if the sum comes out to be greater than 1, then we are in serious trouble. Why are we in serious trouble? Because the mathematics police is going to come and is going to arrest us because we have exceeded 1 in this case. We are not supposed to do that. So there is a problem. So what do? We need to make some change to our formulation. So what is the problem? The problem is probability, and the solution is also fairly straightforward. So this solution is something that we often call in the chaste vernacular of the region as jugaad. Okay, so next time please don't call it jugaad, call it an engineering approximation. Okay, so the solution is, instead of taking a sum, let us take a linear combination of each one of these Gaussians. What is the meaning of a linear combination? The meaning of a linear combination is that one takes a probability weighted sum or a probability scaled sum. So instead of simply adding the Gaussians, n indicates normal distribution or a Gaussian. So instead of simply adding the Gaussians, we take a linear combination. So the pi j's would be the linear combination coefficients. So instead of simply adding the Gaussians, one takes a linear combination of the Gaussians. That's the idea. Okay. Now we need to mathematically justify it because this otherwise looks like a heuristic. So let us look into some properties of this. We are taking a linear combination of the Gaussians here, and the idea is to finally put it in the form of a linear combination of these Gaussians. So we have a summation of these Gaussians, but each one of them is tempered by the linear combination parameter, which is pi j. So how does one do that? One wants to essentially put some stamp of approval that, well, this is mathematically correct on this expression. So in probability theory, one result from the Bayes rule is that we can factorize the marginal. So what we do is, instead of taking p of x, we take p of x given j, wherein x could be an effect and j could be the cause. But then if we do that, we will also need to multiply that or modulate that with the a priori probability of that happening. So how does this work? For instance here, so if we wake up in the morning and find that the lawn is wet, so there could be there, in a simplistic situation, there could be two reasons. One reason could be that somebody had left the tap on, and when the water supply had come, all of it went to the lawn and the lawn is wet. And the other case could be that, well, it may have rained at night. So this is essentially looking at the probability x given the fact that somebody had left the tap on into the a priori probability of somebody leaving the tap on, plus the probability of finding the grass wet given that it had rained at night into the a priori probability of this event happening, that is rain at night. Okay, so if you look at this, so we know that multiplication is commutative, and if you see that I have marked this in red, and just compare terms which are associated with the same color, so this, there is a good chance that there would be a one-to-one correspondence between the formula that we obtain from the Bayes rule and our linear combination formula. Okay, so with this intuition, let us go ahead. So what is the physical significance of what we have specified here? The physical significance is that ij is the prior probability of picking the jth component. Okay, and that is something that comes from the Bayes rule. So if we do a one-to-one correspondence of these two, then this is what one gets. Okay, so the jth model in this case, the model is the jth mean and the jth covariance matrix. So this is the interpretation. Now, what about the posterior probability? The posterior probability is what we often call the inverse probability. So what is the inverse probability? The inverse probability is what is the probability of the cause given that one has an effect. Okay, that is the idea here. So it is something like saying, I want to calculate the probability that it had rained last night given the fact that I observed the grass to be wet, or I want to calculate the a priori probability of the fact that I had forgotten to switch the tap off. The tap remained on and I ended up with the grass getting wet. Okay, so that is the idea. And this is what is called in probability theory as the responsibility. Okay, so the responsibility, what is the intuition behind this? The responsibility is the probability of the jth model accounting for the data given the fact that some event has occurred, that is we have observed it. So this is called the responsibility, that is it is the probability of the jth category or the jth cause. How much is J responsible for the X given that X has been observed? Okay, so it is the in this case, it is the what is the probability that the jth Gaussian, because we are considering a mixture of Gaussians, what is the probability of the jth Gaussian accounting for the observation given that that observation has taken place. So this can again be found out using the Bayes rule. Okay, this is something that we are all familiar with. The probability of j given x can be split up into the probability of x given j into the jth a priori probability, and the denominator is a normalization. We have to do this for all excuse me, all possibilities of this cause. So this is the normalizing factor out here. Okay, and because multiplication is commutative, we can write it in this form as well. So the responsibility in this case, if we just put a, because we have established a one-to-one correspondence of pj being pi j and probability of x given j to be the Gaussian, the jth Gaussian. Okay, so we end up with this. So this is an important formula which we are later going to use in some practical illustrations of the expectation maximization algorithm being what we will use here. Okay, we'll take a conceptual break here, and we'll take an actual break at about 11:15. What the conceptual break is, do you know what Bayes was by profession? It's interesting. He was a man of God, and across the ages, some of the most profound mathematical and scientific discoveries have actually come about as the result of the work of priests or men of God. A perfect example is the Reverend Thomas Bayes. He was a priest, okay, and who did mathematics just as a hobby. Then in biology, genetics, the entire theory of genetics is based on the work of this Austrian monk, Gregor Johann Mendel, okay, wherein he derived the laws of heredity. Then in more modern times, there is this gentleman. He's called Mahan Maharaj. His name is Mahan Mitra. By profession, he's a saint. He is a man of God. He's a monk of the Ramakrishna Mission order. On the other hand, he's one of India's most famous mathematicians. So he's on the faculty of the Tata Institute for Fundamental Research, TIFR. He's also on the faculty of IIT Bombay. So if you look up the IIT Bombay website, www.math.iitb.ac.in, you'll find this gentleman's name. He does mathematics as a hobby, and by profession he's actually a man of God. So Mahan Maharaj is also officially called Swami Vidyanathananda, and he's the recipient of India's top award for any scientist or mathematician, which is the Shanti Swarup Bhatnagar Award. He won it in the year 2011. He's also the recipient of the 2015 Infosys Prize for the Mathematical Sciences. So these men of God, they do science and mathematics as a hobby and make our lives difficult, right? We are engineers. We are not really scientists or engineers. Okay, so with that little mathematical aside, let's look into the role of this linear combination coefficient, which we are calling pi j. So as before, we we started with a slightly filmy example of Lightning McQueen, and there what we did was we took a filmy example. Then in describing the good, the bad, and the ugly, there's another filmy example. Here we are looking at the role of pi j. So what we will call this is the life of pi j, and we'll look at some properties. Okay, so if you remember the movie, in this case, the roles of pi, Piscine, and the tiger, Richard Parker, are sort of inverted, because here we want to consider what the role of pi j is. Okay, yeah, Richard Parker, the name of the tiger. So pi j is a number between 0 and 1, and the sum of all of these pi j's has to be 1 if this is a linear combination parameter. And how and why, this is actually rather easy to see. So if we look at the expression, p of x is defined as not a sum of Gaussians but a linear combination of Gaussians. Then what happens if we integrate both sides? So if we integrate the left hand side, we have an integral of probabilities across its universe of discourse. So what does this end up as? This ends up with 1. What happens if we take an integral on the right hand side? We assume that these functions are well behaved functions, unlike generalized functions like Dirac deltas or unit doublets. So we can interchange the order of the summation and the integral. So we can take the integral inside. If we take the integral inside, we can take it inside further, because pi j is a constant which doesn't depend on the integral. So if we take the integral inside, we have the integral of a Gaussian. And what is the integral of a Gaussian? The area under a Gaussian is 1. This is a property. So if we end up with a 1 here, then what is it that we get as a form of this equation? We get sigma pi j on the right hand side, that is equal to 1 on the left hand side, which is what we wanted to prove. Okay, so something that we achieved as a result of some perspective from engineering is something that we actually end up with here as well. Okay, so we have been able to prove what our intuition was telling us. Now let's take an illustration. Okay, so this illustration is again from Bishop's famous textbook. So in this, what does intuition tell us? Our intuition tells us that there are 3 models. There's a red Gaussian model, there is a green Gaussian model, there is a blue Gaussian model. Now, unfortunately, nobody colors this for us. Okay, unfortunately, what one is given is this. Our intuition is that our model is going to have 3 Gaussians. What we would like to do is we would like to find the responsibility. This is what we actually have to do. This is the ideal situation. This is the ground truth. However, Mother Nature doesn't give it to us. We are given just these. What we have to do is to get these responsibilities. So what is the intuition behind that? So the probability of a point here coming from the red Gaussian should be more. So this representation is actually rather intuitive, because we are representing the color of a point. The color of a point is typically modeled as a 3 cross 1 vector, an RGB value, red, green and blue, where each individual red, green and blue component is a number between 0 and 1. So here, for a point which is here, it is expected to have a color which is close to, in RGB coordinates, 100. So essentially red. And a point here is expected to have a color which is nearly purely green. So in RGB coordinates, it is close to 010. All right, that's green. And a point here is expected to have RGB coordinates which are close to 001, R, G and B. So it's expected to be blue. Now in the region which is close to a place where both of them have joined is there. Yeah, there is a question from Dr. Venkateshwara Rao. Yeah, can you please unmute your microphone and speak it out? Dr. Venkateshwara Rao, K. Venkateshwara Rao.
No, no, sir. No, sir. He is one of the coordinators.
Oh,
You
okay,
please go
sir.
ahead,
Yeah.
sir.
Yeah, I know that there are some
Thank you.
4 minutes left for me to stop talking
Yes,
and
sir.
then take a little bit of break. Yeah. I've got my eye on the
Yes.
because yeah, we are teachers. We sometimes lose track of time. Yeah, thank you very much. Thank you very much, Dr.
Uh,
Venkateshwara Rao. I'll finish in about 4 minutes, and then we'll take a 15-minute break. So in this case, so a point here is expected to have a bluish green color. That is something maybe the R component would be very small, close to zero, but then there would be almost an equal contribution from blue and green. And similarly here, so this is like a bit like the Indian festival of Holi, wherein one takes these holy colors and then mixes them up in certain proportions. So this color as an estimate in RGB coordinates, this is what the responsibility really is. That is, what is the probability of the jth model? In this case, J could be R, the red Gaussian, it could be the green Gaussian, it could be the blue Gaussian. What is the probability that, let's say, the red Gaussian was responsible for explaining this data point? What is the probability for the green Gaussian as its responsibility for getting the color of the green point, and what is the responsibility of the blue Gaussian model for getting the color of this point? So this is actually a pretty nice illustration, and we'll talk about it after we take a break. So here, after the break, we are going to discuss what the basic maximum likelihood estimation problem is. Then, given the fact that some of us are mathematically inclined and one knows that the in a pure Bayesian sense, maximum likelihood estimation is not optimal. Okay, what one should do in a pure Bayesian sense is actually take a map estimate or a maximum a posteriori estimate. What is that? Why do we still stick to maximum likelihood estimation? So these are some of the things that we are going to discuss after the break. Okay, so I'm sure you all might be a little bit tired of me right now. So there'll be a 15-minute break, and I'll start again at around 11:30. And from 11:30, we are going to go till approximately 1 p.m. Okay, so I'll put my, if there are any very quick questions, you can start with that. Thank you, Dr. Minati. Thank you for the very kind words. So if there are any very quick questions, you can please, even instead of putting it in a chat box, you can just unmute your microphones and speak it out. I'll mute myself till I have to answer. Okay, thank you. Samples from that. And the philosophy works the other way around also. If one is given an array of samples, so essentially if one is given a probability mass function, from that it is possible to get an estimate of the probability distribution function, what it would be for a continuous case. How? By simply creating a histogram, and the distribution function, what it would be for a continuous case. How? By simply creating a histogram and then possibly smoothing it out or fitting some model on top of that
This
histogram.
conference will now be recorded.
And well, this is something one can generate samples according to any distribution. For instance, if you look up Narsingh Dev's famous book, so one of the techniques that he describes is that given the probability mass function, one can take the cumulative distribution function or just the distribution function to get a monotonically non-decreasing. Well, it will also work for a monotonically non-increasing function, which gives values between 0 and 1. And then what one does is one generates a random number according to a uniform distribution on the y-axis and then cuts the curve and then drops it down to the x-axis. So the sample there at the x-axis would effectively give us a value which has been taken according to the underlying distribution, which is given by the cumulative distribution function. And what happens if one has a flat surface on top of this cumulative distribution function? The approximation that one takes is one takes an average of the set of values. That's it. So it works. And for a Gaussian, we can get it in closed form using what's called the Box-Muller formula. Plus we have a general formula as well. Well, the ideal case is if the density, the probability density function is indeed the mixture of k Gaussians as models, then one can draw a set of k samples from that. However, the actual reality is that one is just given n observations x of I, d-dimensional feature vectors from a physical process. So Mother Nature gives us just n observations. We assume a model, that is our modeling. Okay, we assume a model which can turn out to be good or bad. And in this case, we assume our model to be a mixture of k Gaussians and we'd like to estimate its parameters. So this is the underlying philosophy behind the process that we are going to follow. So suppose our model, let's start with a simple case. Suppose our model is one-dimensional Gaussian. So these are one-dimensional numbers. So we have a set of capital N numbers and not vectors. This is a simple example. And what is our model? Our model is one-dimensional Gaussian. So what are the parameters of a one-dimensional Gaussian? The parameters are the mean, mu, and instead of the covariance matrix, one has the variance sigma square, or for that matter, the standard deviation sigma. What are the assumptions? One takes a typical assumption of the data points being IID. Now, given my employer, I have a natural tendency to put a T somewhere here, IITD, but believe me, it's not that. It's IID. IID is independent and identically distributed. What is the physical significance of IID? The physical significance is independent. That is, with independence, this allows marginal probability multiplication without considering conditional dependence terms. That is, we don't have to consider terms of the form A given B and then apply the full Bayes rule. We simply take the marginal probabilities and multiply them. So it is a simplification. It helps us to simplify the math as well. Okay, so this is one assumption, that is independence, which allows us to multiply the marginal probabilities. And the identically distributed part, where does the identically distributed part come in from? The identically distributed part comes in saying that each one of these observations has been taken from the same physical process. So if our model was one-dimensional Gaussian, all the samples have come from the same model which is one-dimensional Gaussian. That's the idea. Okay, all have come from the same model. That is our assumption. And how will we do it? This is something that needs a bit of explanation. So look at this. Capital X is our set of n observations which have come from Mother Nature. It has come from the physical process, and this is something that we are given. What are mu and sigma square? These are our set of parameters. Now, please note that it should be reasonable to say that if our model is good, then the probability of getting back this set of capital N numbers from our model, which has parameters mu and sigma square, should be high. This is called likelihood. Okay, so this is called the likelihood. That is the probability of getting back the same set of observations which have come from the physical process or from Mother Nature. And we would want to pose our optimization problem in such a way that find me those set of parameters which maximize this probability. Okay, this is called maximum likelihood estimation. This may not be the most optimal way to do it, but as with most machine learning problems, this should at least be reasonable. All right, that is one of the main considerations. Okay, so I hope everybody is convinced that it is at least reasonable to find the parameters which maximize the probability or the likelihood of getting back these set of points given our model. So this is maximum likelihood estimation. Now, why can it be that these may not be optimal? Because if anybody, all of us know the Bayes rule. The Bayes rule involve, see, it would be optimal in a perfect Bayesian sense if we also multiply this with an a priori probability. That is a priori probability of the parameters, a priori probability of mu and sigma square. Now, so if we know that there is something which is optimal in a Bayesian sense, why don't we use it? The reason why we don't use it is, in many cases, it may not be feasible to estimate the a priori probabilities. For instance, the example that I like to take often is, what is the a priori probability of the moon hitting the earth? First is, this is not a very palatable thought. The second thing is that it is not possible to estimate this as a probability for a very simple reason: this hasn't happened. So we cannot compute the, we cannot estimate the probability even in a frequentist approach in terms of the relative frequency. The second is, we do not have any physical process on the basis of which we can assume this. Well, one question could be, why not take this as a constant and then go ahead with the calculations? See, please note that we cannot even do that. Why? Because there is no evidence to even tell us that this a priori probability would indeed be a constant. So that is the reason, why we take this. So there are many problems wherein we are forced to go in for a maximum likelihood estimate instead of looking at a maximum a posteriori estimate, which is optimal in the Bayesian sense. And in fact, maximum likelihood estimation, well, this is not optimal, but the main point is, it is at least reasonable. And with regard to maximum likelihood estimation, even if it is not optimal, what we often do in many applications is, we take the maximum likelihood estimate and then put it in a constrained optimization framework. We put additional mathematical constraints on top of this problem and then try to solve it, so that, because otherwise MLE is liable to problems such as overfitting, and obviously it's not optimal. So we take other methods to get a solution. Okay, and it is at least reasonable. That's what we have seen. So if we make the IID assumption, this is what we get. Please note this carefully. The independence results in multiplying all of these probabilities without having to consider the conditional probability terms. And the identically distributed part says that all of these, so the model for all of the xi's is the same. It is one-dimensional Gaussian. So this is a consequence of the identically distributed part. This is what we need to maximize. So one important observation is, instead of trying to maximize the likelihood, we often, what we do is, we maximize the log of the likelihood. We maximize the logarithm of this likelihood. Now, what allows us to do this? This is in fact the theory of John Napier. John Napier, as we all know, is responsible for the formulation of logarithms. Okay, why can we replace maximum likelihood with maximizing log likelihood? That is because log of x is an increasing function. It is not equal, but it is equivalent. That is the point. Increasing function, that means it has the same nature. And the second biggest advantage of using logarithms as opposed to other ordinary numbers is that multiplications, which have an increased complexity, now get converted into additions, and divisions get converted into subtractions, which are easier to perform. So the interesting thing is, logarithms, they are due to this gentleman, John Napier, and what he formulated was logarithms to the base 10. And there is something else, logarithm, which are called natural logarithms, the base e. E is named in honor of the mathematical physicist Leonhard Euler, E for Euler. And so there's another interesting point. So Euler is responsible. He's perhaps only one scientist and mathematician who has two fundamental constants named after him. One is, of course, the base of the natural logarithms, and some of my friends in physics tell me that there's something in optics which is called Euler's constant, lambda, something in scattering, I think. I don't remember that too well. But the other interesting thing is John Napier. In the year 2009, I had an opportunity to visit the Edinburgh Napier University, and in the middle of this ultra modern glass and steel structure, suddenly one is hit by a 16th century structure, Merchiston Castle. And the interesting part is the Dean International Relations sits inside this, inside what actually used to be John Napier's kitchen. So they've actually maintained this 16th century castle structure to date. They maintained it very nicely, and this is the entire university is named in his honor. Okay, now let's get back to our original problem of maximum likelihood estimation. So what we are taking is the logarithm. So this is the logarithm of the expression. This is something that we need to maximize. So what we do is we simply substitute the values. This gets pretty dirty even in a one-dimensional case. So we split that into three terms. We have a constant term, just depends on n, and then one which depends on sigma square, and then one term which depends on sigma square as well as mu. So how does one maximize the log of the likelihood? One takes a partial derivative. Variational calculus tells us that one needs to take a partial derivative with respect to all sets of parameters, set them equal to 0. And then what is the next step? The next step is, well, some of us are used to this in mathematics. So suppose we have a function of two variables x and y. We take partial derivatives with respect to x and y, set them equal to 0. And then we do a second derivative test. That is, take del square, all forms of the second derivative, del square f by del x square, del square f by del y square, and the mixed derivative, del square f by del x del y. And then if we call these terms as r, t, and s, one considers rt minus s square and looks at the sign. So if it is negative, we have a maximum. If this is positive, we have a minimum. If this is 0, we are in trouble. So one needs to take derivatives of higher orders. Is this a point of inflection? But come on, we are engineers. We can do something better. There is a very nice technique which allows us to figure out whether something is maximum or minimum. It's very simple. We put it back into we find the extremum and put it back into the function and look at the values of the function around a certain neighborhood. So if this value is a maximum out of inside this small neighborhood, we say that it is a local maximum. If this is a minimum, then we say it's a local minimum. Very simple. So we engineers have a way out here as well. Right. Okay, what are the parameters and how do we find them? So the parameters are mu and sigma square. We need to estimate them. So let us take a partial derivative with respect to mu and set it equal to 0. So this is what we get. After that, the result here is that mu, this is actually something that we knew beforehand. We knew that the maximum likelihood estimate for the mean is going to be the sample mean. Okay, so the maximum likelihood for the mean is nothing but the sample mean. All right, this is something that we knew beforehand. And we'll, if we take a partial derivative with respect to sigma square, set it equal to 0, we reorganize all the terms on the left hand side and the right hand side. What we get is again interesting. What is on the left hand side is the maximum likelihood estimate of the variance, sigma square. On the right hand side, please note this carefully. This is nothing but the sample variance. Okay, it's a point minus the mean whole square divided by n, and we are taking an average. So this is something that we already knew before in terms of our intuition. That is, the maximum likelihood estimate of the mean is going to be the sample mean. The maximum likelihood estimate of the variance is going to be the sample variance. In fact, this tells us how we can fit a Gaussian to a set of points. What do? We take the sample mean and that is the location at which we will plonk the Gaussian down. And the variance or the standard deviation is a measure of the width of the Gaussian and the height also, because the area under a Gaussian is 1. So this tells us how wide the Gaussian would be and where we are fitting it, where we are plonking it down. So this is something that we knew beforehand, and this appeals to intuition as well. Yes. Now, a more general case is we have not one, but k Gaussians. And these are not one-dimensional Gaussians, but these are d-dimensional Gaussians. So what is given? We are given a set of vectors now. Each one of them is a d-dimensional vector. We are given n such observations from either the physical process or whatever Mother Nature has given to us. What is our model? Our model is k d-dimensional Gaussian. So we have the set of means. So there are k of these terms. There are these means mu j, the covariance matrices sigma j, and there is a new parameter here, which are the mixture coefficients. Do you remember the life of pi? Yeah, these are the mixture coefficients. So here we have not one or two as before. We have a set of 3 parameters. We have 3 sets of parameters: the means mu j, the set of all mu j's, the set of all covariance matrices sigma j, and the set of all pi j's, what we will call pi. What are our assumptions? Our assumptions again are that the data points are IID. So IID is independent and identically distributed. As I mentioned before, given my employer, I often have a tendency to put a T somewhere here, IITD, but then that's not correct. This is IID. IID says that they are independent and identically distributed, all samples. That is our assumption. What is the physical significance of the independence? The physical significance of independence is that we can straight away take the probabilities, close our eyes, and multiply those probabilities. What is the significance of identically distributed? It means that the model is the same. Okay, so we have the same model, in this case a mixture of k Gaussians as one, from which we are assuming that each sample has come in. So that is essentially what I have just mentioned before. And how do we do it? We wish to find, so please note the physical significance of this particular term. This indicates the probability of getting back the set of observations which had come from Mother Nature, or whatever have been given to us as a result of the physical process, given our set of parameters. Our set of parameters is the set of, what are these? These are the set of a priori probabilities, the means of the Gaussians, and the covariance matrices. So this is called the likelihood, and this is something that we want to maximize. And as before, we need to check whether it is reasonable or not. Why is this reasonable? Let us look at this probability. That is, if the model is good, then the probability of getting back the same set of observations which had come from the physical process, or which Mother Nature had given us, is expected to be high. Okay, and our problem would be to find the set of parameters which actually maximize this probability. So even though it is not optimal in a Bayesian sense, because we are not modulating this with the a priori probabilities of the parameters. Do you remember why this may not even be possible? The example that I like to give is, what is the a priori probability of the moon hitting the earth? First is, there is no way we can realistically estimate the a priori probabilities in many practical situations. The second is, there is sometimes no compelling reason to even assume this to be a constant or have any particular form, because we have no other information here. So the best that we can do is a maximum likelihood estimate, and at best what we can do is we can append this with some other external constraints to form a constrained optimization problem and then try to solve it. And as before, what we are going to do is, instead of trying to maximize the likelihood, we will equivalently, this is not equal, but this is equivalent, we will maximize the log likelihood. Why? It is the theory of logarithms. What is the advantage? The advantage is that the function has the same nature. So log x has the same nature as x. Okay. And the second biggest advantage is that multiplications get converted to additions, and subtractions get and divisions get converted into subtractions. So it is computationally better. However, this is slightly dirtier. Okay. Because in this case, if we take a log, this log stays outside the summation. Here it can go in because there's a multiplication here. So these expressions get dirty. And in fact, the expression for a d-dimensional Gaussian is even dirtier. All right. So how do we do this maximization? We use variational calculus. We take a partial derivative with respect to every parameter and set it equal to 0. So let's take the first parameter mu j, take a partial derivative. Now, most of the calculus which is based on vectors is actually quite similar to what it would be for the scalar case. It just looks dirty. So this is the expression that happens. We try to simplify this, and please note the term that comes in here. This term is something that is quite familiar to us. What is this? This is the responsibility. So the end result that we cop up with is actually something that we expected again. That is, the maximum likelihood estimate for the mean turns out to be what? It turns out to be the sample mean itself. So gamma j, the responsibility, is a probability. So what is here on the right hand side is a probability weighted mean of all the xi's. So this is something that we had expected before, and this is something that we get. So this is according to intuition. So this is nothing but a probability weighted mean. That's all. And if we make a similar effort for the second parameter, sigma j, we are also going to get something which is reasonably intuitive. That is the value. The maximum likelihood estimate for the covariance matrix will turn out to be the sample covariance matrix. This is again the probability weighted covariance. Okay, so these are intuitive. Now we take the third parameter pi j and take a partial derivative with respect to that, and what we end up with is unfortunately an engineer's worst nightmare. What is the engineer's worst nightmare? We get a 0 equal to 0 situation, which doesn't help us. We are stuck. So what do? We need to go back. So it's not that we have made an error in calculations. Our assumptions are not correct. So we need to make some change in our model. We go back to the drawing board, we need to change our model. Our model was not sophisticated enough to handle this situation. And at the same time, if we have made such an effort to create a model and then also differentiate it, and these expressions tend to get dirty, we would want to utilize all the effort that we have put in thus far into creating that model and only change it slightly. Okay, we are engineers and we are also lazy people, and well, don't call it laziness, give it a technical name, call it the law of conservation of energy. Yeah, that's what we call it when we want to say that we want to procrastinate. This is the law of conservation of energy. So in this case, see, a model is only as good as it can model data. The example that I usually take in this regard is, let's say we are looking at the model for an atom. Then we remember Bohr's model, right? Bohr's model perfectly describes atoms as long as we are considering the hydrogen atom. On the other hand, so if we are considering just the hydrogen atom, then Bohr's model works perfectly in that case. However, if we want to go to other higher elements, helium and above, we need to change our model. So every model involves involves some approximation, and we select a model which is reasonable and is simple enough, because this also is something that comes from computer science, where computer science, it's called Occam's razor, which says that if there is a simpler model which can explain some phenomenon, we go with the simpler model. That is also rather intuitive from a control theoretic point of view. For instance, in a control theoretic point of view, if we have a system with a smaller number of parameters, that is, it is much more pliable. Do you remember that example that I took of trying to invert a large matrix vis-a-vis inverting a smaller one? So what we generally do is, instead of taking a more general model, which might result in a system wherein the system matrix is either singular or gets close to singular, in which case we will not be able to invert it, what we do is we reformulate our model. We do a simplification. We do a, let's say, a row wise or a column wise set of operations on this matrix and get a reduced system matrix, and then try to utilize this. That's the idea. So in this case, we will modify the objective function using a mathematical trick called regularization. This is the method of undetermined multipliers. This is the method of Lagrange's method of undetermined multipliers, wherein we will have the same objective function as before, but take a linear combination of another set of conditions, which quote unquote conditions the optimization problem. That is, the sum of all a priori probabilities, or the linear combination coefficients, should be 1. Now, why is Lagrange's trick very interesting? Lagrange's trick is very interesting because, see, if we want to take a set of partial derivatives, we must take it with respect to all parameters. What were the parameters? The parameters were mu j, sigma j, and pi j. So if we took, so we have already taken a partial derivative with respect to mu j, we got a decent answer. And take a partial derivative with respect to sigma j, we get an answer. We had a problem with respect to pi j. We will see whether we get something in that regard or not, because unlike the 0 equal to 0 situation before, we have a second term which involves pi j. So hopefully we should be able to get a solution for pi j. If we don't, then we will have to rework our model in such a way that we get a viable solution. That's the idea. So in this case, what we do is, well, we have also introduced one new parameter. So we'll need to take a partial derivative with respect to lambda as well. So please note that the first term is independent of lambda. So if we take a partial derivative with respect to lambda, what do we end up with? We just end up with sigma pi j equal to 1. That is what we end up with, which is one of the conditions that we wanted to impose anyway. So this is where Lagrange's trick comes about. So we need not evaluate these combination coefficients. So it is called Lagrange's method of undetermined multipliers. That is, we need not determine the lambdas as a part of the optimization procedure. Okay, so this is the trick. So what happens if we take a partial derivative with respect to sigma mu j? This doesn't affect our previous estimate because the new term is a constant with respect to mu j. Similar is the case with respect to sigma j. So this is law of conservation of energy. We didn't have to change our previous estimate. If we take a partial derivative with respect to pi j, we hope to get some non-trivial solution, and our hope is based on the fact that here we didn't get anything for pi j, but we have a term here. And with respect to lambda, this doesn't really work because it's not necessary, because this is the constraint to be imposed. So for the third condition, let us just reorganize all of these terms. We multiply both sides by pi j to get a familiar looking term. This is what we get here, and we make that simplification, and then finally just a bit of algebraic significance. Here what we end up with is lambda equal to minus n. We put it back and we get pi j as simply the relative number of numbers in the jth cluster, so to say, divided by the total number of points. This is an interesting observation. So we at least end up with a proper non-trivial estimate for one of the parameters that we sought to optimize on. That's the idea. So there's a little bit of a story here. So there are intertwined stories, or rather histories. So Lagrange was actually not a Frenchman. He was a Italian who was in France at the time of the French Revolution, and apparently he just escaped the guillotine because of the help that he got from the famous scientist of his time, Lavoisier. But Lavoisier was unfortunate enough to be, he's one of the most famous people to be guillotined, and which is such a waste, because Lavoisier is responsible for the discovery of two fundamental elements, right? Nitrogen and oxygen, which are 99% of the air that we breathe. And well, where is Lagrange's story interspersed with that of Fourier's? Fourier's story is that Fourier was an engineer like us, most of us. He was actually a civil engineer, and the story, Fourier's story, is something like when Napoleon Bonaparte invaded Egypt. So he took along with him a team of scientists and engineers. Fourier was one of them. And the story goes that one hot afternoon, when he was staring at the pyramids, he was working on a problem in heat transfer. Fourier got this idea, well, if I have a set of periodic functions, can I construct functions as a linear combination of a set of sinusoids? So that was Fourier's observation, and Fourier did a couple of back of the envelope calculations and found that, well, he was able to utilize his series. Now this was a real technical jump, because the other series, for instance Taylor series, which was popular at this time, see, Brooke Taylor's theory said that, see, Taylor series is very restrictive. Why is Taylor series restrictive? Taylor series is restrictive because it expects the function to be analytic. What is an analytic function? That is, derivatives of all orders should exist. And in Fourier's new series, it did not have any assumption regarding the derivative. So Fourier thought that, well, he has ended up with a series which is wonderful. Now, unfortunately, Lagrange, the mathematician, was his teacher, and being a self-respecting teacher, he actually never really allowed Fourier to achieve or to get any credit for his wonderful observation till almost just a couple of years before he passed away. Because, see, Lagrange as a mathematician was worried that Fourier had actually not put any existence conditions. It was only after Dirichlet came up with a set of conditions which would guarantee the existence of Fourier series. So there was no real mathematical basis for Fourier's series. So it was almost throughout his lifetime, it was always called Fourier's hypothesis rather than the Fourier series. Okay, so this is how Lagrange and Fourier are related. So Lagrange is a sort of a villain of Fourier's story. However, Lagrange has many other very important contributions to mathematics. Lagrange multiplies is one of them, and in fact the extension to, if you're familiar with machine learning and you're familiar with the KKT conditions of an SVM, the Karushkun-Tucker conditions, this actually is based on a bit of theory wherein Lagrange extended his idea of undetermined multipliers not just to a set of linear equalities, he extended that to a set of inequalities as well. So this is actually rather interesting. So the KKT conditions, the basic underlying mathematical theory, again is due to Lagrange. So that is how these, okay, so little stories aside, what we'll now want to do is we want to get an expectation maximization framework for a Gaussian mixture. So what is one given? One is given a set of n observations, n points in d-dimensional space. This is what has come out from the physical process. This is what Mother Nature has given us. What is our model? Our model is a mixture of n Gaussians. What are the parameters? We have three sets of parameters as we have seen before. The set of means of the Gaussians, the set of covariance matrices, and the linear combination parameters. How can we make an initialization? This is interesting. We can in fact initialize these with one iteration of the k-means algorithm itself. Okay, please note that in the formula for the responsibility, it involves Gaussians, that is exponentials in both the numerator and the denominator. So therefore, such a dirty mathematical expression, it is not possible to estimate the parameters, that is the mu j's, the sigma j's, and the pi j's in closed form from that. So what do we have to do? We have to take recourse to an iterative algorithm, and any iterative algorithm needs a good initialization. So we can run one iteration, we can run a couple of iterations of k-means on top of this data. We can estimate the sample means as being the initial values for the means of the Gaussian. We can put an initial estimate for the sample covariances by looking at the radius of each cluster, and additionally we can get an estimate of the pi j's as the relative number of points in the jth cluster with regard to the total number of points. So it is possible to find an initial estimate of the log of the likelihood. So this is what I just happened to mention. We evaluate the responsibilities using the current set of the parameters. In the maximization step, we re-estimate these parameters using the current values of the responsibilities. So the formulae that come here are, so this is our definition. We define n of j to be this, and note these results. These are results which we have just proved from our parameter estimation. So we estimate the new mean as the weighted sum of the sample mean. We estimate the new covariance matrix as the responsibility weighted average of the sample covariances, and we estimate the new value of the linear combination coefficient to be nj by n. And we evaluate the log likelihood once again. If this value is quite similar, of course, to some level of accuracy to the previous value that we started off, we end our iterations. If not, we go ahead with another iteration. And we can also check for convergence of the parameters themselves, mu j, sigma j, and pi j. If they are very similar to what it was in the previous iteration, then we stop. Otherwise, we take another iteration. It's interesting. This also is provably optimal. In fact, this example again, this is not it is provably convergent, but not provably optimal in a global optimum sense. Here again, because there is no guarantee that the function that we are considering is convex, so we might get stuck up at a local optimum. However, just like k-means is provably convergent, the EM algorithm is also provably convergent. So here again, let's start with a mixture of Gaussians, and we initialize. So this is in 2D space, and these two, let's call it the red Gaussian and the blue Gaussian. We make an arbitrary initialization at an arbitrary location with an arbitrary center. So the mu j's are arbitrary. We make an arbitrary assignment for the sigma j's, which is the covariances, and initially we assume that the variances along the two dimensions here in the two-dimensional case are equal. So a Gaussian, when looked at from top, looks like a circle. So if the variances are different, we'll have more variance along one axis as compared to the other axis. So it will end up being an ellipse. So this is our initialization. So what is the first step? We estimate the responsibilities. So in this case, so as it was for the k-means case, it was a 0-1 indicator variable. So points that were closer to the red model would be colored red. Points that were closer to the blue model would be colored blue. In this case, we are substituting that 0, 1 case with probabilities, responsibilities. So we have a gradation. So points that are closer to the blue model would be expected to be blue. Points that are closer to the red model would be expected to be red. And there is a gradation of colors here. So this is the expectation maximization for the Gaussian mixture case, and we recalculate the parameters. So here you can see that they end up being ellipses. Okay, and we again do the estimates, we re-estimate the parameters, we again do the estimates, and we estimate the parameters again. And in this example, we end up with convergence at L equal to 20 iterations. And this is what I talked about in terms of initialization. That is, we use k-means to initialize it. Okay, because any iterative method needs a good initialization, and that's what we end up with. Now comes the last part of the talk today, which is one of the most practical implementations or most practical applications of the online k-means, which is the background subtraction. So here, what is the model? The model is the color or the gray value at a pixel in a video is given by a distribution which is modeled as a mixture of adaptive Gaussians. In other words, so if X is a color, it is a RGB vector. So we take this as a mixture of Gaussians. This is what we have studied. So the probability of a pixel probability of a color coming in at a pixel location given the RGB value is modeled as a mixture of Gaussians. So here again, we'll adopt a filmy terminology. So if this is color, then X is a vector. It is a 3x1 vector, a RGB vector, or if it is a gray value, then one is looking at 50 shades of gray. Well, not 50 shades of gray, but about 5 times that number, because typically we have 1 byte per pixel, and 1 byte means we have a set of 256 gray levels that the gray value at a pixel could take. Okay, now empirically the number of Gaussians is taken as a number between 3 and 5. This is chosen empirically because of the computational complexity of this entire procedure. So just to keep things in perspective, this is taken as a value between 3 and 5. We'll give an illustration. I'll give an illustration of this assumption and a little bit of a justification. Then we are considering a mixture of Gaussians, that is multiple entities can appear or disappear, and yet this will be adaptive. That is, the model should remain the same, although its parameters should change with the lighting conditions. That is, it should be an automatic procedure. And we can also see this is an unsupervised technique. So this is not a ground truth. So what we are doing is, because any iterative procedure works well if we have a good initialization. So if we are given, let's say, 100 samples before, if you are given some history of the color or gray values at a particular pixel, let's say for the first 100 frames of the video, we can take that as being representative of the entire video, or we can sample from in between and then use that to initialize our parameters for the mixture of Gaussians. That's all. It is just for an initialization. This is not a separate training phase as it would be for a supervised learning methodology. I'll give an example. So suppose we have a video camera that is looking at the sea. We have put it on the seashore and it's looking at the sea. So how will we model the gray value of a pixel which represents water? So most of the while we would expect the color of the water to be relatively dark. So one would expect that there would be one Gaussian in this distribution of gray values which peaks around a low value, let's say around 10, close to 0. So this is the first Gaussian in our mixture of Gaussians. Now, additionally, because there are waves in the sea and waves could break. So when waves break, there is a big splash and the gray value, it's lighter. Okay, so when there is a bit of that splash, the color is a bit lighter. So we can assume that there is another Gaussian there for a case where a wave breaks, which is perhaps centered around, let's say 127 or so, half of the range. Okay, so we have a justification for two Gaussians. Now it could also happen that there is a specular reflection. So a ray of sunlight falls on the water and there is a very bright reflection out of that. So we might have a third Gaussian as well there, which is very close to 255, let's say around 250 or so. So this is a justification for using a mixture of three Gaussians to model a pixel which represents the seawater. Okay, so this is it. So this K is actually in our hands, and empirically what Stauffer and Grimson advise is take that between 3 and 5. This seems to model most natural phenomena quite well. Okay, then as we look at some other details of this algorithm, there is a heuristic at a particular pixel to decide which one of the Gaussians is most likely to contribute to the background. So we use a heuristic here. We'll describe these heuristics and pixels. So if a pixel which matches a background model, so there are two possibilities, either it matches or it doesn't match, right? So if it matches, then we have a set of steps to do. If it doesn't match, there is another set of steps. And something which doesn't match is possibly the foreground, something which matches is the background. And foreground pixels we can group together using either any simple method, either region growing or split and merge, or simple a spatial application of k-means will also do the job. Okay, I think I've talked enough. It may be better to actually see a couple of examples and then try to motivate the theory. So I'll jump ahead a bit and let's see a couple of these examples, and then we will describe some of these theory parts. So let's see some results with a different set of parameters here. So so at this point, what I'll do is I will play some of these videos. So I'll stop sharing the slides. I'll start sharing the videos. So let me do that. So I'll start sharing the media player. So soon enough, you should see the media player here, and let's open a file. Okay, I hope you can see this video. Have a look at this video. This has been taken with a surveillance camera. And in this video, what can you see? You'll see that there is a parking lot and there is a black SUV which is backing out from its parking lot. There are lots of things in this video which are moving. The black SUV is backing out from the parking lot. Then there was a bit of wind that day, so that leaves of this tree are also swaying slightly in the wind. This is something you may not be able to see very closely from the resolution of this video, but yes, they are moving, and this shadow is also moving slightly. Plus, there are these two loafers who are roaming about the parking lot without a care in the world, as if they have nothing else to do. And you might be able to recognize one of these loafers, the one with the blue shirt and dark gray trousers. Yeah, that was me. I was a bit healthier at that particular point in time. Now, what is the difficulty associated with trying to automatically find which the foreground pixels are and which the background pixels are in this video? The difficulty is that, for instance, the black SUV would intuitively correspond to the foreground because that is moving, that is temporary. But then nobody tells us that that SUV is black. We don't have this information beforehand. Plus, we'll also note that when that black SUV backs out, like here, there is a strong specular reflection. So this part is almost white. And there is also a change in color because when the black SUV goes into the shadow region. Plus, you have these two loafers and their shadows, of course. They're roaming all around the parking lot. So they are moving. When can we consider something which is moving to be a part of the foreground? When can we consider it to be a part of the background? Plus, the leaves of these trees are also swaying slightly in the breeze, and therefore the shadows also would be moving slightly. Now, please note that this is something which is very close to the ancient Indian philosophy of the Jad and the Chetan. So, what is this ancient Indian philosophy? Some people also like to, some electrical engineers like to give an interpretation. This is a Fourier way of life. This is a frequency interpretation, that is slowly changing entities. The low frequency entities are typically expected to be the background. For instance, if I take a video and water is flowing, or let's say leaves are swaying slightly in a breeze, or let's say there is a flag fluttering, it is still expected to be the background. On the other hand, things which change drastically are expected to be part of a foreground. Okay, so this is, so for a foreground background subtraction, please note that simply taking an XOR will not work. Will not work because simply doing frame differencing, it will identify which are moving and which are not. Now, everything that is that is moving is not really the foreground, because the background is also expected to move, but then move only slightly. This is the important part. So this is a characterization of the background. Let's say there is a surveillance camera which is looking at a coffee shop in an educational institute like IIT Delhi. By the way, the coffee shop is, in a pre-pandemic scenario, it is a point where students are most likely to be found. So it makes sense for a surveillance camera to look at this portion. Okay, so the students who are walking all around would be a part of the foreground. That is expected. So if the camera is looking at a couple of trees which are swaying in the breeze, then that is expected to be a part of the background. So if the Indian flag is there, it is fluttering in the breeze, it is expected to be a part of the background. Now, on the other hand, if the students come, take a cup of coffee and then stand at the coffee shop for a very long period of time, then they are expected to become a part of the background because they are not moving. And the moment they start moving, they should again be a part of the foreground. So do you understand what is the need for this entire procedure to be adaptive? Okay, this is the perspective behind why we want to have something as being adaptive and why we want to model it as being adaptive. Okay, let me show you. Yeah, there's somebody has a question or a point. I'll mute my microphone and please speak. Okay, that might have been a glitch, but that's perfectly fine. So let me try to show some other video here. I'll try to show this particular video. So let's try to play this particular video. Let us play the background modeling of this particular video. Now I'll just pause this video at this moment. Please look at the first frame. The first few frames. All right, it will come back to this. This is a modeling of the background. So as you can see, although initially everything was moving and then our initial estimate was pretty noisy, it has been reasonably able to adapt itself to modeling the background. The background includes the swaying leaves, It includes the two loafers when they stop and then they turn around. So you've seen this video playing again. So when you see this video playing again, let me pause this and get back to this part. So when it plays again, you'll see that initially everything is a part of the initially the background estimate is not correct, but then gradually it has adapted itself. See, it is adapting itself to the fact that the SUV has now gone off. So you'll now see that this becomes a part of the background. You'll see a little bit of ghosting. So these two loafers, when they stop briefly, they become a part of the background and then again become a part of the foreground. So the background model is able to adapt itself. Now the complementary piece of information here is in the foreground. Complementary piece of information in the foreground. Let us play the foreground now. So the foreground is represented by the white pixels. So you'll gradually see that things which were part of the foreground now start getting absorbed into the background if they are not moving. So there would be some noisy pixels here and there, and you'll see that when the two loafers stop, they again become a part of the background, but then they become a part of the foreground once again because they're the only moving entity. There are a couple of pixels here which wrongly get classified, but look at it when the video replays, when it restarts. Okay, initially everything is a part of the foreground, but then you'll see that gradually all of this part, all of the parking box, everything gets absorbed into the background model. Okay, and in the end we end up with these two loafers and their shadows essentially being the foreground. So this is one. So all right, I'll share a little secret since some of us are teachers. The first time I had heard about this particular Stauffer and Grimson algorithm, I was pretty excited. I wanted to have perspective into how this works. Okay, so what did I do when I wanted this perspective? When I wanted this perspective, I gave out an assignment. Okay, because we teachers don't work ourselves. We get work done, right? So these are different assignments with different sets of parameters. I'll just play another one with a different set of parameters. So first, let's look at the background model for this. So here you can see that once again, you can see how it's adapting. So with the little bit of ghosting, so the black SUV suddenly becomes a part of the background when it stops. But then when it starts moving again, it becomes a part of the foreground. So the background model adapts itself. So the information is there in the model. It is stored in the model. It doesn't disappear. But then because of a probability threshold, it does not appear as a part of the background. So you can see by this point, it has learned the background quite well. So as the video replays, you should be able to see how the background with this set of parameters, it's able to estimate the background quite well. And for that matter, in this case, the two loafers, only when they stop, yeah, at this point, but when they turn and they start walking again, they can become a part of the foreground. So the background model rebuilds itself. It re-estimates itself in an adaptive manner and then goes ahead. So let us see the corresponding results for the foreground. The results for the foreground are as follows. So here, the foreground pixels have also been colored according to their original colors. So you'll see this part gradually dissolving into the background, so that after, as we go ahead with time, only the two loafers remain a part of the foreground model. The rest has disappeared into the background model. Of course, there are a couple of noisy pixels, but then we know that we can tackle them through any sort of median filter or any other similar heuristic. Let's see when it resets. Initially, the black SUV and the two loafers are a part of the foreground model, which is expected. And as this region is uncovered, gradually it becomes a part of the background. When the SUV goes off, gradually it becomes a part of the foreground. Briefly enough, the two loafers, when they stop, they'll also become a part of the background, but then again, they'll become a part of the foreground. So this is with another set of parameters. Let me try to show this with yet another set of parameters. Let's see the background model first. Okay, so here you'll see that the white pixels, what is changing here is the frame number. The white pixels indicate the foreground and the colored pixels indicate the background. So here you can see that the background estimate is relatively good. There is a certain amount of confusion where these two loafers walk in front of this shaded region. You can see this little bit of a confusion here, but then you'll also see it adapting itself well. So when the video replays, you should be able to see this again. So initially the foreground has the black SUV and its shadows. Then the two loafers, there's a bit of confusion when this black SUV enters the shadow region. There are some noise pixels here. There is some amount of confusion here as well, but you'll see that the model is gradually able to adapt itself relatively well. So let us see the complementary information for this case as well. So the complementary information is the foreground model for this particular video. So in this case, the background is all white, the foreground is colored. This is a complementary piece of information. So there is some confusion where the SUV goes into the shadow region, some confusion where these loafers also enter the shadow region. So you'll consistently see that these two loafers, at least most pixels corresponding to that, here they are going through the shadow region partially. So there is a bit of confusion, but you can see that the background model is fairly well learned, and the foreground model is something which is not the background, is the foreground. That is also learned relatively well. Let us see another set of parameters. See the background model first. So the difference in this video is that the original frames are also shown side by side with, so in this case you can see the background model. So gradually the two loafers have become a part of the background. This is the original video, the one on the left, the frames. They'll become a part of the background when they stop here, for instance, but then again they'll blend into the background. So you can see that the background model has learned itself relatively well. So you can see how it's learning when the video replays. So very quickly it's able to adapt itself into identifying which are the pixels corresponding to the foreground and which are the ones corresponding to the background. The background pixels have been painted over in color, whereas the foreground pixels have been taken out. So once again, we'll see the complementary piece of information here. Sorry. Okay, so here the white pixels correspond to the foreground. And here you can see that it adapts itself relatively well to the background pixels here. And in the end, only the two loafers should be a part of the foreground model. There is of course quite a bit of noise here, but then you'll see that this model has been able to adapt itself and learn the set of situations quite well. You'll see this again when the video replays. Yes, here when there is a lot which is a part of the foreground. Of course, in addition to the noise, there's this black SUV and the background is getting learned nicely. There's a bit of a glitch when the SUV goes into the shadow region, but then overall it's able to adapt itself quite well. Okay, so once we have seen all these examples, let's go back to our set of slides and let's get back to some theory part of this particular algorithm, that is the Stauffer and Grimson background subtraction or background modeling algorithm. So the slides should come on pretty soon. Let us look at where the adaptability comes in from. So we have an online approximation to k-means to update the Gaussians. Why do we need to do it? Well, if this pixel process can be assumed to be stationary and doing expectation maximization for a time window would be costly. So therefore we have an approximation. So the Stauffer and Grimson background subtraction algorithm is a approximation to k-means. And in fact, those of you who are from the domain of control theory would say that, well, what is the stability of this algorithm? It seems to be too heuristic based, which is indeed actually true, because for stability, one typically needs good noise models for a Lyapunov stability analysis, which are actually a bit difficult for two-dimensional data, because we often have what is called structured noise, okay, in the form of, let's say, uncovering of regions of the image and also regions getting covered, okay, occlusions. So it is a bit difficult to have this. So therefore one has to take recourse to heuristics. And what is a substitute for getting a Lyapunov stability analysis? What Stauffer and Grimson did was to let it run. This is a 1997 paper, IEEE Transactions on Pattern Analysis and Machine Intelligence. They let their algorithm run for months at a time at MIT, and that was across day and night. So you had different lighting conditions, it was across different seasons, and the algorithm didn't crash. Okay, so there's a good evidence that, well, this process would be relatively stable. That's the idea. Okay, so there can be two situations. Either there is a match with one of the K Gaussians and they modeled it as lying between 2.5 sigma, or there is no match. Okay, so instead of plus minus 3 sigma, they took a heuristic to take it as 2.5 sigma, which is perfectly fine. So if there is a match, then they updated the three sets of parameters, updated the mean, they updated the covariance matrix. Here, there's actually a bit of approximation that is again involved, which is in trying to approximate the covariance matrix with one parameter. We'll talk about that if there is a bit more time. And there is one parameter here, which they call alpha, as being one knob to turn. Alpha is the learning rate. So alpha, if alpha is 0, that means this parameter rho would be 0. So if you look at rho, it is a linear, so the previous mean would be the new mean itself if there is no learning. So the two extreme cases are rho equal to 0 and rho equal to 1. If rho equal to 1, every time it is learning, it is taking the new evidence and it is picking that up. And in a normal situation where rho lies between 0 and 1, because by virtue of this being a linear combination, it's a linear combination of the past estimate and the current estimate. So this is true for the covariance structure as well. So this is interesting. And the prior weights of all the Gaussians is adjusted in such a way. We'll discuss this if time permits once again. And why does this need to be adjusted? Because of one pathological situation where there is more than one best matching Gaussians. For instance, when the two best matches are equidistant on both sides of the gray level. So this is the idea. And if the new gray level doesn't match any one of the background models which are modeled by a Gaussian, then that means something new has cropped up at this pixel, and this information needs to be put into our model. So what do we do that? We take the least probable of the Gaussians. So what we do is, out of the k Gaussians, we sort them in decreasing order of, this is a very neat heuristic, we sort them in decreasing order of pi by sigma. Pi is understandable, that is something which has a higher a priori probability would be expected to be weighed a little bit better. But why are we putting sigma into the mix, and why do we put it in the denominator? Now remember, this is again the ancient Indian philosophy of the Jad and the Chetan. Sigma indicates variability, and for a background the variability is expected to be less. So if something has a large variability, if it is put in the denominator, this results in a smaller number, so the weight would be reduced in such a case. Okay, so it's a set of some very nice and practical heuristics which Stauffer and Grimson take recourse to. Now, couple of these points here. The Gaussian with the most supporting prior evidence and least variance corresponds to the background. So this is what I mentioned before. We order the Gaussians in decreasing order of pi by sigma. Greater probability and less variability. So less change suggests that it is more amenable to being a part of the background. The first B distributions out of K, we take that to be our background model. If it matches one of them, it's a background pixel. If it doesn't, it's a foreground pixel. We just put it above a particular scene dependent threshold. That's all. So this can also be modeled. However, there are some issues like computational complexity. So this algorithm put into perspective, each pixel is treated differently and in an adaptive manner, which is perfectly fine because this makes this algorithm being amenable to parallel processing. So each pixel can be processed in parallel. However, on a sequential computing platform, this means a large amount of compute complexity because we have to process each pixel separately. So we'll need some heuristics to reduce that, like group together a set of pixels, process a group of pixels instead of one pixel each. What is another plus point? Objects are allowed to be a part of the background without changing the existing background model. We have seen numerous nice examples of that in the videos that I have shown. There are some disadvantages. It will not work well for, let's say, a discotheque sort of environment where the lighting changes drastically. This is meant to handle slow and gradual changes, as you have seen. Then the initialization of the Gaussians is important. The bad initialization, this algorithm doesn't work too well. And there are many parameters which need to be selected smartly. And of course, with different regions, there could be different models, and plus other heuristics could be put, like objects in shaded regions would normally not expect, one would not expect much of noise to be there as compared to ones in the well lighted regions. Then there can be an extension to handle more than one model, that is for different times of the day. Like there could be one model for the forenoon session, one model for the afternoon session for a surveillance camera, one for nights, and there could be additional model for different seasons as well. So that's the idea. And with about 14 minutes left for the presentation to end, I guess I'll stop talking at this particular point in time. And please feel free to ask questions, seek clarifications, point out errors, and all of that. Okay, so Dr. Minati Mishra, thank you very much for the kind words once again. So if there are any other point, please, any points, any clarifications, please unmute your microphones and
Sure.
speak out. Yeah.
I want to know, actually, K means in machine learning, K means receives so much of attention, but there is a similar algorithm K methods. So, is there any application area where K methods will work?
This is actually a very nice question. This is actually, as I had mentioned, this is the same family of algorithms. So it basically depends on the application. See, in terms of k-means, the generic, the what is common between all of these algorithms is that first there is a central descriptor of data. The central descriptor could be a mean, it could be a median, it could be a mode. Okay, so k-means has mean as a central descriptor of data. A k-medioids would have a median as a central descriptor of data. So in cases where it makes more sense to use a median, like for instance for nonlinear noise filtering, one often takes recourse to a median filter rather than a mean filter. A mean filter is linear and it sometimes smooths out portions of noise which are according to a linear model. So a nonlinear model may work better in isolated noise pixels, for instance. So it basically depends on the application. So some application, you're absolutely right. A k-medioids algorithm would be expected to work better than a k-means. So this family of algorithms has two entities. One is a central descriptor of data, the mean, median, or mode. The second is, so what were the two parameters? The parameters were mu j, which were the prototype vectors. So take the mean or the median, take a central descriptor of data. Then the other parameter was Rij. Rij, we knew we could either take a binary indicator variable or one could take a continuous variable which takes values between 0 and 1. So what are the two possibilities for, what are two common possibilities for taking that variable between 0 and 1? We could give it a probabilistic connotation. So there are probabilistic k-means formulations. We could also have a fuzzy method there. So in fact, the fuzzy one, at least empirical evidence seems to suggest for applications such as geospatial modeling. Okay, for multispectral images, fuzzy c-means apparently works very good for land usage data. So apparently there is some empirical evidence that fuzzy c-means, as it's called, that particular variety seems to work better for land usage data taken with multispectral images in different bands by satellites. So this again depends on the application and empirical observations, such as what works better for what situations. Okay, madam, you're absolutely right. But there is no definitive answer to that. It completely depends on the application and the set of assumptions. Very nice question. Thank you.
Thank you, sir.
Any other point or any other comment, clarification? Please feel free to unmute your microphones and speak. Yes, please go ahead. Please feel free. Or I guess it's got a bit late and instead of food for thought, thoughts are turning to thought for food, right? It's very close to lunchtime. So depending on how the session chairperson, Dr. Venkateshwara Rao and Professor Ravichandra and the other organizers, you take a call here. I'm around.
Sir, you have demonstrated your presentation through several different parameters. No, that experiment. So how do you select the parameters?
Yes. That's actually a very difficult question. My first answer, more in a funny manner, would be to say that I didn't select them. Like, we are teachers, right? We don't work. We are very lazy people. We don't work. We get work done. as it's called in the chaste vernacular of the region where I come in from, हम काम करते नहीं हैं, हम काम करवाते हैं. So we get work done from students. So how were these parameters selected? So on a more serious note, so what I asked students to experiment with was the amount of data that they were taking to initialize the mixture of Gaussians. That is, so they heuristically selected the number of Gaussians. So told them to take the number of Gaussians between 3 and 5, which they were perfectly fine with. Then some of them took no prior initialization. Okay, so they simply started off with random Gaussians. They took a mixture of 3 to 5 random Gaussians with random parameters. So that's why you see some differences in the sets of in the results that have come in. Some of them have taken, let's say, the first 100 frames. Some of them have gone the extreme. They've taken every frame of the video for this particular training phase. This is not training per se, but this is the initialization phase. So they say that there is no one part of the video which I can separate out, and in order to get representative statistics, so I'm taking information for each pixel from all the frames of the video. So they've taken information from all the frames, they've used it to initialize the Gaussians and then let it run on this particular video itself. So those set of parameters they've taken in this way. Then the threshold, that's another parameter. How do I decide how many Gaussians to consider? The parameter B. So the parameter B, they took a heuristic, which one adaptive heuristic is the relative proportion of the foreground pixels to the background pixels for any frame of the video. As you saw, it's about 1/10. Okay, the maximum number of foreground pixels for the video. So this video is QSIF resolution. So that's 384 by 288. So about, they took 10%. Okay, that is one of the heuristics. Some of them also tried to be a bit more adventurous. Some of them tried to be a bit more conservative in fixing it by hand. So you'll see different manifestations of changing the parameters. So the assignment I gave out was that take these parameters as knobs, which you'll adjust yourself with your hand and then try to check it out. Then try to check it out. Whatever gives good visual results, you can present that. So this is where the parameters come in. I hope I've been able to answer your question, madam.
Yes, sir. Yes, sir. Thank you so much, sir. It's a very good presentation. Thank you.
Thank you, Dr. Mishra, ma'am. And we invite the participants for the interaction. We have got for 5 more minutes.
Exactly. So last 5 minutes to get back at me.
Good afternoon, sir.
Yeah. Yes.
Sir,
Dr. Singh.
yes, sir. Thank you. Sir, my question is, most of the time I saw in the some research papers in literature, they have used KNN as an pre-processing method for the data clustering.
Yes.
Sir, how it can help the for the prediction accuracy? Because I think 90%
Yeah, Dr. Singh,
time
that is a very practical question. That is a very practical question. A couple of clarifications. First is, although these names seem alike, they're actually quite different. KNN is a classifier. It is in fact the simplest possible classifier. It says that whatever is the nearest prototype, you put it there. So KNN is a variant. The similarity in terms of the words is also because of the similarity in terms of what basically happens. That is a classifier. Now, if I am simply using k-means as a pre-processing method, you're absolutely right. It is used as a pre-processing method because there are nonlinear clustering algorithms as well. Now, the state-of-the-art nonlinear method is something which is nowadays used in many applications, something called TSNE. Okay, so TSNE works on a nonlinear principle. It is, for instance, one often uses in a linear manner. One would like to look at if data is multidimensional, one would like to project the data onto lower dimensional spaces and then have a look at whether this data indeed is getting clustered or not. What TSNE does is it uses the T distribution, and what it does is it takes data onto lower dimensions in a nonlinear way. So k-means is still used as a pre-processing based method because of its reduced time complexity. Typically its time complexity is less. It is used as a first cut method to at least check if the data is clustered or not. If the data is indeed clustered, then some other techniques such as a classification technique or other data processing may be done in a worthwhile manner. All right. So it is used as a pre-processing technique. You're absolutely right, Dr. Singh. Yeah.
Sir, it means KNN is different. KNN is like a classifier.
KNN is a classifier and
Yeah.
k-means is an unsupervised algorithm. So KNN is a supervised algorithm. It just says that you can take the k nearest neighbor, so the output of the classifier. So if I take the distance of a point from different classes, it says that if I've got a set of, let's say, L classes, I'll take k out of them, the ones which are closest. So instead of picking one as the best, I may want to spread the net a bit wider because of noise. I might end up picking the wrong one. So instead of picking one, the best one, I pick up k good ones and then go ahead. Yes.
Okay. Thank you, sir. Thank you.
Okay, Dr. Singh. Thank you. I think Professor Ravindra has also come in.
Sir, finally we have come to the end of the session, sir. Dear participants, if you have any kind of queries or anything to ask, sir, you can please write to us. We shall forward the same to sir. And that was really nice sessions from you, Professor Datta Roy, sir.
Thank
Sir,
you very much, sir. Yeah.
Right from the beginning onwards, I was observing you. You are such a cool person, and everything was very nice, sir.
Come on, sir. You're being
Yes,
too
yes, sir.
generous.
Yes, sir. Yes, sir. These words are out of heart, and these words represent the participants also, sir. I am speaking on
Thank
behalf
you very
of them.
much, sir.
Yes, sir. Yes, sir.
Thank you very much, sir. And
Thank you.
it's been a nice experience. So I'll take everybody's leave. Thank you very
Sure.
much. So everybody has my email anyway. So you can give a reference to this STTP at SRIT
This
at
conference is no longer
Anantapuram,
being recorded.
and you can send me an email and I can get back to you. And Ravichandra sir, thank you very much for the opportunity.